This year, students at Hopewell Valley took part in several different science-related competitions, two of which we're going to talk about today. One is called U.S. First, and one is called the Conqueror of the Hill. First, we're going to talk about U.S. First, and I believe we're going to watch some tape from when we were at the competition at Temple University a couple weeks ago. There you go. Brett.
Okay, here we see the students conversing on the robot, which you'll see in a few moments. Right now, we're just preparing it for the final launching. You can see in a few moments you'll be able to see the rink, and you'll be able to see where the objective puck and floppies are placed. Here we're just doing the final preps on the robot. The final objective of this competition would be to place as many floppies as possible above 8 feet and on the so-called puck. Now this puck is set on casters, and it can be pushed from side to side. And it's set up in an alliance format, whereas you're assigned a team to work with, and the best traits of both robots are fully utilized in getting the puck on the opposite sides, in the opposite alliance. So that is, if you wanted to place the puck away from whatever color you were, and if you look in the picture, you might see some colored stands. Those colors represent the alliances. And you'll see like a line down the middle of the field, and that would be the border line between the teams. The way which we proposed to accomplish this goal is we were given what they call a Spark kit. And the Spark kit included some basic components to get us going. And this included some Bosch drill motors, a transmitter and receiver, including an onboard computer, which included 2 basic stamps, which are small microprocessors. It also included a significant amount of hardware, including bearings, just about anything you can think of that would help us get going. In addition to this, if we needed a few more extra materials, we could go to a small parts catalog. We were allowed a certain amount of parts from this small parts catalog. And so what you see on the robot, with which these students are working on, is a compilation of this Spark kit and the small parts from small parts. Now, you'll see we're all rushing out to the field here. This was a last-minute, just a last-minute repair run. We all got it together though, and got it out on the field for. We gave it a good run. You'll see all the students are very interested in robotics, and many of the students look forward to robotics in their field. And
now you can see the arena where the actual competition took place. There are 2 teams on each side of the arena, and we're in the red team or the blue team, where you have a partner that we work with, and the whole goal is to get the floppies up off the floor. They're kind of like pillows, and hold them off the floor at the end of the 2-minute match. And for everyone that's off the floor, we get 1 point. If they're 8 feet over the floor, we get 3 points. If the puck's on the other side of the field, you double your score. If the robot actually gets on the puck, you triple your score. So there's a lot of strategy involved in the placement of your robot and the placement of the floppies. And you can see at the end of the match, when the 2 minutes are about up, everybody tries to get their floppies up high, trying to get them over 8 feet off the floor. There are many different approaches to actually accomplishing the goal. And that was the end of the match, I guess, because everybody's kind of looking relieved that the time is up. You can see our human player celebrating. I guess we must have won that one. I don't even remember what the score was.
As a whole, it was really a group effort. Everybody tried to get the best, as I said, the best traits of each robot. So you'll see where sometimes one robot will go for one objective, where another robot will split off and go for a different one, maybe one concentrated on securing that puck we were talking about, and another one was securing the floppies above 8 feet. So you'll see the real objective of this competition is the teamwork which inspires between the two teams. And of course, there also is the engineering challenge, which would be, of course, underlying the whole competition.
Each school has a corporate sponsor, at least one corporate sponsor, that's supposed to supply the monetary support, but also the engineering support that's needed just to get your ideas into action, actually to build them. And some schools have many engineers working with them. Some schools have 1 or 2 engineers working with them. Some schools brought 60 students. Some schools brought 5 students. So it's not as though the teams are equally matched in personnel, but everybody's learning a lot. Everybody's having a good time in the competition, and it's really not who comes in first, but who actually has a robot that does what they plan for it to do, accomplishes the task. It was huge this year. There were 60 teams, almost 60 teams there. It was at the new Temple at Apollo, which is a large gymnasium. The arena was much larger than we're used to in the past. We were at Rutgers University, which was a smaller competition. And it was kind of overwhelming when you first walked in and saw the cheerleaders and the bands and the banners and the mascots and that sort of thing. But when you got down to it, there was an awful lot of learning taking place.
A lot of the learning that did take place took place actually in the pits, where we were presented with real design challenges, where some of our designs had problems with them, as any design would. And the certain failures of the designs were expressed in the mechanical stresses, and in the pits we got to go in there and fix these problems and find ways to prevent them in the future. And I think that's where the real learning took place, when we got to go in there and see what went wrong and see how to fix it, get it done in time to go out there and compete again. I think that was the real challenge of this competition.
Well, the other tough part is that the challenge is given in the second week of January, and your robot has to be packed up and in a warehouse the last week of February. So you really only have 6 weeks to design and build the robot, test it, learn to drive it, make sure it works, and then give it away. And then you wait until the competition comes, and when you arrive, you get to uncrate it and see if it looks like what you remembered. So it's truly a time challenge also. The students were working daily on this, Saturdays, Sundays, days off from school, every day after school. It takes a lot of dedication, a lot of effort, a lot of hard work, along with their regular schoolwork. They weren't excused from school to do any of this. So they really have to be interested and really have to focus on what we're doing and get things done when we're all together.
I guess we could probably show you a few of the aspects of the robot now. You get an up-close look if we go over here. We'll show you a few of the electrical components first. Down in here, these blinking things, those are the functionality monitors of the speed controllers. They control the drill motors directly under my finger here. They drive, that's the primary drivetrain of the robot. Over here we have this pump that supplies the pneumatic pressure. Down here, this is our lift. This here is a van door motor. That's from, like, if you've seen van doors, which have are sliding and they can be opened and closed automatically by a remote control. This is the motor that would do that kind of functionality on a van. It's a very high torque motor, which is why we selected it for this application. This specific application is the lift that was to get our floppies above that 8 feet to get those extra points. Moving on now to the arm, you'll see another one of these drill motors. You can see we used 1/4 inch chain and rigged this up so we can tilt the arm forward and back to grab onto one of the floppies with this
Grabber
mechanism here. This actually is powered by a pneumatic cylinder, which the pump is driving. This actually, we had a rather innovative design, and a lot of them used the Velcro that was on the floppies, but we chose to just kind of snatch them up with this this kind of pincer design. Also, you'll see This year, we used a lot of metal structure, a lot of metal working was involved, a lot of hard student work. These actually, all the pneumatics are controlled by solenoids, which are electrically controlled air valves that we can open and close this. And I don't know if we can.
I think we're ready to demonstrate.
A little demonstration.
Okay.
We'll just tilt the arm out, show them that that's the motor powering up.
I'll drive it forward a little.
I'll just grab onto the floppy, close it, lift it up, just pull it up there, and just right in. And then from this point, we can go on and pick up the other floppies. And we also have the functionality of lifting these floppies above 8 feet. The whole system itself runs on 12 volts. And you'll see how we have fast movements this year. That's one of the problems we have in the last years. We were a little slow in the field. So this year, you'll notice we're very fast. It's kind of hard to get used to in the beginning because it's the movements are very rapid and capable of accomplishing a task very rapidly. Now, just to talk about the other functionalities of this robot, we not only can put floppies from the ground, we can also have the functionality of pulling them out of other robots. Some robots have baskets similar to this, but with very large netting. And we could actually grab that netting and pull a floppy out of the netting, thereby taking some of their points away. There we go. We can just pull it right out of another robot as well. We also had a human player, who's Elton over here. We just got him in the picture. And Elton had the responsibility of throwing the floppies into the basket. And this is something that other teams depended on heavily. We didn't really depend on that heavily. More what we concentrated on was the ability to pick the floppies right off the ground and do a backward slam dunk right into our basket here. And if we could just lift that basket up a bit, show them the altitude it's capable of. If you just run it over. Okay.
This was a slow process at the end of the 2 minutes, but the idea was when you saw the match ending, move the floppies up as high as you could and get them up that 8 feet so that you could have 3 points per floppy.
This was the final objective. And speed was not so much of an option, not so much of an objective here.
Very good.
So you can see we can get quite a bit of altitude on this.
Okay. Well, thank you very much. Thanks, Brett. I think we're going to go on to the Conqueror of the Hill competition. Mr. Seibel's over there with students that were involved in that, and they're ready to explain that competition. Thank you very much, first team.
This year we were involved in the Conquer the Hill competition. It's a statewide competition whereby you are given objectives and some household materials where you build a machine that's going to perform a certain task. This year's task was to take 3/4-inch disc magnets and to get them as close to your opponent's end as possible. This year at our school level, we took our 2 top teams and went up to Murray Hill, New Jersey to compete against 90 other teams for possible scholarships and other types of awards. This year it happens that we had a team score fourth place at the competition, and they also won some graphing calculators for their efforts. Our second team that went up was in ninth place this year. We'll have the two different teams demonstrate their projects and explain how they work.
For our project, we decided that we were going to avoid confrontations actually on the hill because as there's many vehicles were very powerful coming across. So we went with more of a catapult type method where we actually fire our arrow up and over the opponents and have it land just at the end of their wall. It's connected by a string to the base, so it's considered part of the same project and was legal. Our actual arrow was nothing more than a piece of wood with a magnet on each side, and our ramp here would pull back on a rubber band, just a simple firing bar that would shoot up and fling our arrow up and over their project, all the way against their back plate, while the base of ours would stop any vehicle coming here, while ours would go all the way to the back plate, hopefully giving us victory. And it worked out pretty well when we actually ran it. Should we give a demonstration?
Yeah.
All right. Talk about it.
We had to, the starting mechanism was a rod with a nail in the center of it at the competition, and you had to have a string. It couldn't be a rubber band or anything else. It had to be a string with a loop on it. And that's what we have right here. And the rubber bands are connected to a firing bar, and then the arrow, so-called, is put in the slot right here. And we got disqualified once because our string was over the line, is over like maybe a centimeter or so, so all the string has to be tucked back behind the 12-inch line.
Yeah. Our machine took kind of a beating in the last rounds of the competition, so it hasn't been firing 100% all the time, but it should basically show you the idea that it will hopefully fly up and land somewhat near to their back plate. We lost some of our support in our last round. The machine is started by releasing the line, which has tension on it. All right, and that's pretty much the method we used. As you see, it delivers it fairly near to the back wall on the opponent's side. And actually in air, it gets enough air to clear most projects. So for most of our, 18 rounds we played, we delivered it successfully right around that area, which as you can see is well past this red line, which is as far as an opponent's vehicle can get because of our base. So we'd have the advantage and win that match. It also gives us a lot of offensive points because we got it almost all the way to the end.
And our other team, representative today is Frank Swoll, who'll explain to you his design.
Okay, basically we used a design that we had seen last year at state competition that did very well, so we figured we'd try something like it this year. It's basically opposite of their design. It more or less tries to extend itself down the hill using like the main body rather than launching some type of projectile. And it uses like a scissor like type accordion design with rubber bands that will extend it like this under the pressure of the rubber bands because they wish to contract. And we placed magnets around random places, and we also added some defensive things in the front, like a tall shield to block any other projectiles, and also some nails here that serve to protect our project that when collisions would occur. So I guess we'll see what works.
Hold it.
And it's usually a little bit faster, but right now we're kind of working with some underpowered rubber bands. So normally it would have sprung down much quicker and hopefully reached the other end before the other team's vehicle even got moving.
Okay, thank you, gentlemen, for your demonstration of your projects.
Mr. Simon, we can play a little tape. You want to talk about it?
Sure.
Go ahead. David.
This tape is from our school competition where different teams attempted their different types of vehicles against each other. At the school level this year, we started out with 30 teams of our own. As I said before, 2 of those teams moved on to the states, the 2 teams that you saw here before. But this year's school competition was our biggest ever and was very competitive. The teams that competed were participated from the regular physics classes, the honors physics classes, and the AP physics classes. This competition serves us well in the physics department in that it helps us to achieve some of the New Jersey standards that are going to be tested in the years to come for our pupils as they prepare for graduation. In the future, we hope that the competition can maintain its level that it achieved this year, and we also hope that the enthusiasm that the students showed both at the school level and at the state level continues. We've had relatively good success at the state level. We've had teams in the past finish as high as second place, and we've also had teams that have scored some of the special awards. For example, last year, Frank and his partner scored Best in Show for a novel design that the judges had not seen before.